Good morning, it's Alex here again. Now this part we are looking at the design of shaft based on the failure of shaft due to bending only. So now, shaft subjected to bending moment only. Okay, so based on this simple bending equation and the strength relationship, we have the bending moment M, the moment of inertia I. This time is moment of inertia I, not polar moment of inertia, because now we are looking at the bending about the x-axis or the neutral axis. Now sigma would be the bending stress, and y is the vertical distance that we measure from the neutral axis or from the center of gravity or from the center of the shaft to the outermost layer of the shaft. So m is the bending moment in Newton meter. I is the moment of inertia, meter to the power of 4. Sigma is the bending stress due to the bending moment. Y is the vertical distance from the neutral axis and is measured in meter or in millimeter. So we have the relationship for the bending equation. Okay, when we have sigma max here, that means the maximum bending stress, we will take the Y max. And then for the minimum bending stress, we will take the Y minimum. For the case of shear stress, tau max over R max, tau min over R min. Now for this bending stress, you have this. Okay, then for the stiffness relationship, we have M over I equals to E over R, where E is the Young's modulus, R is the radius of curvature. So the bending moment M, the moment of inertia I, the elastic modulus or the Young's modulus or the modulus of elasticity, Newton over meter square, and R, the radius of curvature. The moment of inertia. So this is for solid shaft. Okay, so now this is torsion about z-axis. Okay, now we are looking at about x-axis and y-axis. So if you take I-XX, that means the bending would be occurring about the x or either the y. Okay, so then this would be 64 for a solid shaft, XX and YY, remember. So the moment of inertia for the hollow shaft, you have this divided by 64. Okay, so for cantilever, now we are looking at the condition of the maximum bending moment. For cantilever, you have this as the cantilever fixed at one end and free at the other end. If let's say, for example, we have the point load acting at its free end based on the diameter of the shaft D, then this is your bending moment diagram, which you have learned it in your mechanics of engineering materials. So this would be your maximum bending moment, that is by taking moment about this point here. Okay, this point here. So you will have W multiplied by L. So that is your maximum bending moment about this point here, the fixed end. So this is for the point load W. So if it is for the uniformly distributed load for UDL, then the maximum bending moment would be taken as omega L squared over 2, where omega here is referring to the UDL load, which is Newton per meter length. So for 1 mm length, so you will have the UDL multiplied by 1 mm length, that you will be able to convert it back to Newton. Okay, so this is your maximum bending moment for cantilever with UDL load, omega L squared over 2. Now then for simply supported beam, okay, simply supported at both ends, if you have a W acting at the center, then we will take the maximum bending moment as WL over 4. How you get a WL over 4? So, which you should have learned in mechanics of engineering material as well. So, based on these two unknown reactions here, with the load W acting at the center of the beam. So, the load here can be taken as equally distributed among the two supports here, which should be taken as W over 2 and W over 2. So if you take the maximum bending moment, the moment about this point here, the center point, so you have W over 2 times L over 2, that is half the length, if the length here is L. So that is why you have a maximum bending moment of W, which is in Newton, length over 4. So this is a simply supported beam based on point load. Now, if it is having a point load that is offset, that means not acting at the center, then if you were to take, okay, the reaction or the bending moment about this point and also about this point here based on the load of W, you will get both sides of the reaction, one as WB over L, the other one as WA over L. And then the maximum bending moment will be given as WAB over length L. Okay, so this is both the case when it is subjected to point loads or concentrated loads. So if it is for UDL, okay, so the maximum bending moment would be omega L squared over 8. Remember, this is omega, and that is W. Okay, so this is in Newton, and this is measured in Newton per meter. So that will be the maximum bending moment for the case of a uniformly distributed load. Thank you very much for this section. We will continue, or we will see again during the next section. Thanks a lot, and please, any comments or any questions, please put on my comment section in my YouTube for the shaft design. Thank you very much, and see you again soon. Bye bye.